coming back to Global Education Zone, and in this episode we are going to be dealing with a concept called differential calculus. Wow. Now this is a topic which I very much like. It's a very interesting topic for me because differential calculus, it is kind of like the boss of mathematics. There are a lot of concepts which we need to deal with in differential calculus, and in this um course, rather in this playlist, right, no, in this particular what's it called again in YouTube, videos and playlists. Yes, playlist. In this particular playlist, I before this video, preferably, I assume that I've inserted a video on the fundamentals of differential calculus. So today we're just going to be dealing into questions and solutions. So I've done like almost like 3 videos on the fundamentals of calculus, both in this playlist and in other playlists of this channel. So you can check out those videos in this channel, and let's do continue. Let's deal with a particular question involving differential calculus. So we have different concepts which you can actually address in them. One of the concepts in calculus is limits. So yeah, let's evaluate the limits. 4x cubed plus 3x squared plus 2x minus 2. Now, if you are a white student, you will ask me limits where. Now, this is the limit of x approaching what? 1. So that's the limit, and that is the key to us getting the answer of this question. Now, basically, in this particular question, the first thing we are supposed to do is we'll break down these terms. So each of them is this is the limit of a sum, right? Now we'll change it to the sum of their limits. Yes, how? So that will equal to what? The limit of, let's pick the first term. Limit to the limit x approaches 1 of 4x squared 4x cubed plus the limit x approaches 1 of 3x squared plus the limit x approaches 1 of 2x plus limit x approaches 1 of what? Minus 2. Now, for starters, the limit of a constant is the constant itself. So basically, the limits of minus 2 will be another constant, which is 0. So the limit of a constant is 0, obviously. So basically, but this limit of a power of x, we are just going to substitute the value of x, because a limit is basically the value of a particular aspect of a function, which is the power of x, and that x, it is basically the value that variable approaches, no matter what it is. So no matter what x is, it will still approach 1. So we can just approximately say x equals 1. So that's what we'll substitute here. So the limit is as simple as substitution. Just understand the concept. So we have 4 x raised by 2, that's 1 raised by 3 plus 3 1 raised by 2 plus 2 times 1 plus 0. So because I said the limit of a constant is another constant, which is 0. So the limit of any constant is 0, and 0 is also a constant. So then that becomes 4 times 1, that's 4, plus 3 times 1, that's 3, plus 2, that's 1, that's 2, plus 0. So at the end of the day, that our limit becomes 4 plus 3 plus 2, that is 9. We have a limit of 9 here. So that's the solution of this question. Now, you often find more difficult questions involving a limit. We are going to be ready to tackle that. But let's have a peek at calculating limits from first principles. So in this question, let's look for the limit of x approaches 0 of 3x squared. So we are looking for these limits in accordance with first principles. Now, the first thing we are going to be noting here is that this is a 3x squared term, right? So in this case, basically, we have to basically say y equals 3x squared. Y equals 3x squared. So we are going to introduce the left hand side, because that y we are looking for the change with respect to another value, right? So we are looking for the change of y with respect to x. If we are looking for the normal method, for the shortcut method, we'll just say the y dx is equals to what? 3x. The y dx of 3x, that's 3 times dx. 3 times the x square dx. So that equals what? 3 times derivative of x squared is 2x. 3 times 2x, that's 6x. But from first principles, we have to take it slowly. That will equals to y plus change in y is equals to 3x plus change in x squared. That y plus change in y y plus change in y equals to 3. That's x squared plus 2x change in x plus change in x squared. At the end of the day, we have when we subtract y from both sides, we have change in y equals 3x squared is cancels out. That's change in y equals 2x change in x plus it is equals to 6x change in x because we open the bracket plus 3 change in x squared. So if we divide through by change in x, we have change in y over change in x equals to what? 6x plus 3 change in x. But in this case, we are saying change in x approaches 0, right? That means change in y with respect to change in x equals what? 6x plus 0 here. And that 0 does not account for anything, so we discard it. So change in y change in x equals 6x. That's the limit of y with respect to x is 6x. And that's because that is a function on its own that is dependent on x itself. So the function I'll leave you with this knowledge that we'll close the chapter with the knowledge that the gradient of a line is a constant, whereas the gradient of a curve is a function of the variables that contain that or consist that curve, which is x. So which is often it could be a function of x, it could be a function of y. So it depends on what value. So let's talk about implicit differentiation. That's a concept which I very much like to introduce to students in calculus. Now I will be having a special course on calculus, hopefully very soon. Having a special course on calculus where we will talk about the various wonders and various wonderful things you can do with calculus itself. So, but before that, let's move on to implicit differentiation. I want to talk about implicit differentiation. We're talking about the fact that we have a mixed terms. For example, let's say 3x squared y plus 4y squared equals 10. Now, in normal explicit differentiation, you can have your x terms and y terms separate. But in this case, where your x and y are mixed up in the same term, so this is quite a different story entirely. So, but it's still easy. So all you need to do is you differentiate with respect to x separately and take the other variable as a constant. Then differentiate with the next variable and take the first as constant. So you alternate it, and that's how it goes. So let's start from the first one. We'll differentiate. True. So let's the differential of this one. We'll differentiate each term with respect to x. So we're looking for. So when we differentiate each of these terms with respect to x, we will not differentiate each of them with respect to y. So let's start from x. That will be, let's differentiate with respect to x. That will be 3x squared. So the x component of this, the x component, that will be, let's differentiate through respect to x and take y as constant. So that will be 3 dot the derivative of x squared, that's 2x. 3.2x dot y. So that is with respect to x plus 4y squared. The derivative of this is a constant, that's plus. Okay, rather we'll take y as a constant, yes. And when we differentiate a constant, I mentioned earlier that it will give us 0, right? Plus 0 equals 10. Derivative of a constant is 0 equals 0. This is the x component of the derivation, and then let's go to the y component. So we derive every one of them with respect to y now. So 3x squared y, that's the derivative with respect to y, that's 3x squared plus differentiate with respect to y, that's 8y equals 0. So then we add the x and y component, that will be equals to 6xy plus 3x squared plus 8y equals 0. That's the derivative of that expression with respect to x. So obviously, I hope you understand that concept. And basically, that's all for today's class. If you want more on differentiation, there are other episodes, there are other videos I've made in this channel in in-depth details on differentiation. And hopefully, I'm saying very hopefully, very soon I will make a special course on differentiation and calculus. And not only are we going to be exploring the theoretical background, we are going to be exploring the practical approaches of calculus. Why calculus is a very wonderful tool in our everyday life. Thanks for watching.